one of the pretty cool things that we can do with the power series is that we can actually differentiate and integrate. Now, consider the power series, the sum, n equals 0 to infinity of Cn times x minus a to the n, which is the general form of a power series, centered specifically at a. Now, this will have both an interval and a radius of convergence. We want to keep that in mind. Now, I'm going to go straight to a theorem here. Now, if this power series, the same power series I'm talking about up here, this general form of the power series, if it has a radius of convergence such that the radius is greater than 0, so right now I'm looking at r, that's representing our radius of convergence, then the f, or the function f, that's defined by f of x equals c0 plus c1 times x minus a plus c2 times x minus a squared plus so forth, etc., out to infinity, is differentiable and therefore continuous on the interval. And the interval we're talking about here, specifically there over the radius of convergence, or the interval is defined by the radius of convergence, means centered at a, which would be a minus r up to a plus r. And the following two facts are true. d dx of f of x is equal to d dx of the sum, n equals 0 to infinity, of Cn times x minus a raised to the n, which is equal to the sum, n equals 0 to infinity, of d dx Cn times x minus a to the n. All I did is I moved the d dx inside the sum. So what this is actually telling me is I can take the derivative, or I'm about to take the derivative term by term, the sum of all these individual derivatives. Well, that's going to be equal to the sum, n equals 1 to infinity, of n times Cn times x minus a to the n minus 1. Now notice I started now at 1 rather than 0. If we left it at 0 when n equals 0, I'll have 0 times all of that, so it's just 0. So the 0th term, the very first term, when I sum it up from n equals 0 to infinity, is equal to 0, so it just drops out anyway. That's why I start the sum, start the index, at 1. Another thing that's true is that the integral of f of x dx is equal to the integral of the sum, n equals 0 to infinity, of Cn times x minus a to the n dx, which once again I can take the integral and move it inside the sum. So this would be the sum, n equals 0 to infinity, of the integral of Cn x minus a to the n dx, which this is saying I can integrate term by term. Just like a few moments ago we said we're going to differentiate term by term. Well, this is going to be equal to the sum, n equals 0 to infinity, of Cn times x minus a to the m plus 1 over m plus 1. And you see here, let me fix that so it's a little bit more readable. And see here, it's okay if n equals 0, because I don't have anything that's undefined, and when n equals 0, it's not equal to 0, so that term doesn't fall out. So, the radii of convergence for the power series in both 1 and 2, that's these guys right here, are both r. Okay, it's both the radius of convergence that the regular power series had. So if my power series normally had a radius of convergence from, say, -2 to 2, when I integrate and differentiate, it will also have, well, I said radius, but if the radius was 2, when I integrate or differentiate, it will also be 2. The interval, if it was from -2 to 2, will also be -2 to 2. But just like when we looked at the interval before, we need to check the endpoints. Again, when we integrate or differentiate, we need to check those endpoints again. Because what was an open interval on the interval convergence may now become closed or half open or whatever combination there. So we still need to consider the endpoints on the interval. However, the radius, if the radius was 2, it would be 2 here. If the radius was 1 before you integrated or differentiated, then the radius would be 1 after you integrate or differentiate. So, even though the radii of convergence has not changed, which is what I just got done talking about, the interval of convergence might change. Okay, we need to check those endpoints. Differentiation and integration only applies within the interval of convergence. So as soon as I go outside the interval of convergence, I can't say that they're equivalent anymore. If I could integrate the integral of f of x dx, if f of x I can represent as a power series, and I integrate the power series term by term because it's easier than the original function, that only applies, that result will only apply if I stay within my interval of convergence. If I go outside, then it has no application. So I want to find the intervals of convergence for both f and f prime given f of x equals the sum n equals 1 to infinity x to the n over n squared. So I'm going to start off with f of x equals the sum n equals 1 to infinity of x to the n over n squared. That implies f prime of x equals the sum n equals 1 to infinity of d dx x to the n over n squared, which is equal to the sum n equals 1 to infinity of n times x to the n minus 1 over n squared. Of course, this will cancel, make it a little bit simpler, which is the sum n equals 1 to infinity of x to the n minus 1 over n. Now notice here when n equals 1, this is defined and it's not 0. So I didn't lose a term by taking that derivative. If this original series was n equals 0 to infinity, which it couldn't have been because I have n in the denominator, but if the denominator was slightly different and I ended up with n equals 0 to infinity, if I was able to do that, then that first term when I took the derivative would in fact cancel out. So I lose that first term. Okay, so here's my original function, and here's what the derivative is. So let's start off first with the original function. Let's take a look and see if we can find the radius and interval of convergence. So for the radius, I'm going to take a look at the ratio test. And I'm going to take a look at the limit as n goes to infinity of x, absolute value x to the n plus 1 over n plus 1 squared times n squared over x to the n, which equals a limit as n goes to infinity. I'm going to rearrange these once again just so that it might be easier to see what's going on. N squared over n plus 1 squared, which equals the limit as n goes to infinity of the n cancels. I'm going to have x times, this is n over n plus 1 all squared. Well, in the limit, this goes to 1. So this is just the absolute value of x, which needs to be less than 1. That gives me the interval convergence of negative 1 to 1, but I need to take a look at those endpoints. So for x equals negative 1, I have, remember I'm dealing with f of x, not the derivative yet. I'm going to have the sum n equals 1 to infinity of negative 1 to the n over n squared. Well, gosh, that looks like an alternating series. So to show that it's an alternating series, let's go through those steps. First thing I need is I need an to be positive for all n, which it is, because an here equals 1 over n squared. Check. I need an plus 1 to be less than an. We'll see an plus 1 would be, you see, 1 over n plus 1 squared. It needs to be less than 1 over n squared. Well, that would then imply that n squared is less than n plus 1 squared, which clearly it is. But if we take this out one more step, we have n squared less than n squared plus 2n plus 1. Cancels out. Implies 0 is less than 2n plus 1. Remember, the domain for n is 1, 2, 3, 4, and so forth. So this is never negative. So check. And the last thing that I really need is I need the limit as n goes to infinity of an to be 0, which it is, because if I take a look at the limit as n goes to infinity of 1 over n squared, that is in fact clearly 0. So check. Therefore, this f of x, well, I shouldn't say f of x. I'm going to say therefore the series will converge by the alternating series test when x equals -1. So I know that'll converge. Now for x equals 1, I'm going to take a look at that. Let me see here. Yeah, I can fit it in right here. For x equals 1, we have the sum n equals 1 to infinity of 1 to the n, which is just 1 over n squared. That's a p-series with p greater than 1. Therefore, that converges. So I know that's going to converge. That then tells me that the interval is in fact -1 to 1. So I know f of x, being represented by this power series, will converge for x on the closed interval -1 to 1. Now, what about the first derivative? What about f prime? Okay, so f prime, the first derivative of x, we said was the sum n equals 1 to infinity of x to the n minus 1 over n. So let's take a look and see what the radius of convergence is, see what the interval is. So again, I'm going to use the ratio test. I'll take a look at the limit. As n goes to infinity of the absolute value of x to the n, that's x to the n minus 1 plus 1, over n plus 1 times n over x to the n minus 1. And again, I'm going to rearrange this slightly. That's going to be the limit as n goes to infinity of the absolute value of x to the n over x to the n minus 1 times n over n plus 1. And you know, I do that every time in case you haven't figured that out yet. But the reason I do it is more so you can see a little bit more clearly what I'm doing. There's no requirement that you do that. If you just want to do the cancellation, you know, if you say, well, gosh, that's the same as that, that's fine. The point there is simply I do this because I think it may be easier for you to follow what I'm doing. So this is going to be the limit as n goes to infinity. Absolute value of x to the n over n minus 1 will give me just x times I have n over n plus 1. And the limit n over n plus 1 will go to 1. So this is just actually just simply equal to absolute value of x, which must be less than 1. Now, what we need to do is that gives me an interval of -1 to 1, the open interval. So I need to check those endpoints again. So for x equals -1, I have the sum n equals 1 to infinity of -1 to the n minus 1 over n. That is the alternating harmonic series, which we know converges. So I need to take a look at, for x equals 1, that will give me the sum n equals 1 to infinity of 1 to the n minus 1, which is just simply 1 over n. That is the harmonic series. Therefore, I know that it diverges. That means that the interval of convergence is, see, -1 was included, so it's going to be -1 to 1 on the half open interval, which was different from our original function, which was convergent on the closed interval. So when I took that derivative, I ended up with a slightly different interval of convergence. But notice both of them have a radius of 1. The radius didn't change. But the endpoints on the interval of convergence did change. All right, let's use a power series. Let's use power series differentiation to prove that the first derivative of e to the x actually is e to the x. Now, the power series for e to the x is equal to the sum, n equals 0 to infinity, of x to the n over n factorial. That is e to the x. That would then imply that d dx of e to the x is equal to d dx of the sum, n equals 0 to infinity, of x to the n over n factorial, which is, of course, equal to the sum, n equals 0 to infinity, of d dx, x to the n over n factorial, which is equal to the sum, I'm going to write it this way just this one time, n equals 0 to infinity, of n times x to the n minus 1 over n factorial, which of course n equals 0 is going to wipe it all out. So this is going to be equal to the sum, n equals 1 to infinity, of n times x to the n minus 1 over n factorial. Now this will actually reduce. So this is going to be equal to the sum, n equals 1 to infinity, of x to the n minus 1 over n minus 1 factorial, because the n will cancel with the n and the n factorial. Now, when that happens, I can relabel this. I can say, well, gosh, when n equals 1, I get x to the 0 and 0 factorial, which is a reminder, 0 factorial is 1. So this is actually going to be the same as the sum, n equals 0 to infinity, of x to the 0, whoops, not x to the 0, I'm sorry, x to the n over n factorial. So when x equals 1, this becomes 0 and this becomes 0. So I can just simply redo this as a sum, n equals 0 to infinity, of x to the n, because when n is 0, I have a 0 in the exponent and a 0 in the factorial. But that is e to the x. Therefore, d dx of e to the x really is e to the x.